So let's imagine that I have this apple and I'm going to apply a force to it. So here's my apple and I apply a force of 5 newtons. So I push on the apple this way. So I push on it like that. What acceleration does the apple have? Well, let's imagine that the force then that I push on it is 5 newtons. Let's assume the apple has a mass of, let's say, 100 grams. So what's the acceleration? Well, we know F equals ma. A equals F over m. 5 newtons divided by, now let's put the mass in kilograms. Why do we have to do that? We'll see in just a second. 100 grams, converting it to kilograms, 0.100 kilograms equals what? Well, 5 divided by 0.1 is 50, 0.0. Now what is a newton divided by a kilogram? Well, let's remember, a newton is a kilogram meter per second squared. Now, if we divide that by a kilogram, the kilograms cancel, and we end up with units of meters per second squared. So this would be 50 meters per second squared. Why is it important to put our mass in terms of kilograms? Well, if we were to take a newton and divide it by a gram, that would be a kilogram meter per second squared divided by a gram. Well, we can't cancel out the units. We would have to convert kilograms to grams or grams to kilograms to cancel that out to get our units in terms of some kind of unit that we would expect for an acceleration, meters per second squared. So, when you want to put numbers into a calculation, typically you will always want to put them into the standard SI unit, and then you'll be able to cancel them out. And that gives you something, kind of a very easy thing to keep in mind. You don't necessarily, although you might want to, you don't necessarily have to always remember what are the forms of all of these different units, and we're going to see many of them as we go along. That a newton is a kilogram meter per second squared. You do need to remember that it's a force, but a force, you know, is a mass times acceleration. And if you don't remember what it is, you can always remember, well, I know F equals ma, so the units of force must be a mass times acceleration. Mass is a kilogram, acceleration meters per second squared. Oh, so a newton is a kilogram meter per second squared. But also, if you take the units of force and divide by units of mass, you necessarily have to get the units for an acceleration. And if you put the SI units for force and mass, you will get the SI unit for an acceleration. So that tells you if you take a kilogram divided by, a newton divided by a kilogram, you've got to get a meter per second squared. Because you know the SI unit for force divided by the SI unit for mass must give you the SI unit for acceleration. Okay, so it's nice the way that works out. Just make sure that you always put your quantities in terms of the SI unit, and then the other units will always work out very, very easily. All right, great. Well, there we go. So 50 meters per second squared, that's the acceleration of the apple. What's the direction of the acceleration? Well, the direction of the acceleration has to be the same as the direction of the force, and so we know the acceleration is going to be in the same direction with a magnitude then of 50 meters per second squared. All right, let's put some different numbers in. Let's imagine that we have a plane here with a mass of, let's say, 3.10 times 10 to the 4th kilograms. The engines are pushing on the plane, getting it ready to take off. It's going down the runway, and let's say the force from the engines are, the net force is then 3.70 times 10 to the 4th newtons. Let's see if we can figure out what's the acceleration of the plane. Well, we know F equals ma. We'll assume that this is the net force acting on the plane. There could be other forces. Actually, we obviously know there are other forces acting on the plane. We'll talk more about those later. But just for the sake of argument, let's say that this is the net force. This is the mass of the plane. So we know the acceleration of the plane is F over m, which is the net force, 3.70, times 10 to the 4th newtons, divided by the mass, 3.10, times 10 to the 4th kilograms, which leaves us with an acceleration, dividing that out, of 1.19. Now, what is a Newton per kilogram? Well, again, Newton, the SI unit, kilogram, SI unit, force over mass, that must give us the SI unit for acceleration. Even without breaking Newtons down into its constituent units, we know that must be meters per second squared. Well, we already saw that from the last problem anyways. There we go. So the acceleration of the plane is 1.19 meters per second squared. Let's imagine that Dr. Evil is flying this plane, so we've got Dr. Evil in here sitting as the pilot. Dr. Evil is going to accelerate at the same rate as the plane, so Dr. Evil has got an acceleration of 1.19 meters per second squared. Let's see if we can figure out what is the force that must act on Dr. Evil to make him accelerate at 1.19 meters per second squared. Well, let's imagine that he's got a mass of, let's say, 78 kilograms. 78 kilograms. So, what is the force on Dr. Evil, the net force? Well, it's got to be his mass times acceleration, so that would be 78 kilograms times 1.19 meters per second squared. We multiply that out, and what do we get? We get the net force is 92.8 kilogram meters per second squared. Now, you might remember that's a Newton, or you just might think, I've got the standard SI unit for mass times the standard SI unit for acceleration. That must give me the standard SI unit for force, which is a Newton. There we go. 92.8 newtons. Now, let's just think for a second, what is it that is exerting the force on the pilot to make the pilot accelerate? Where is that force coming from? Is it coming from the jet engines, the plane's engines, or what? What is it? Well, think very, very physically. What is it that is pushing on the pilot, making the pilot accelerate? It's actually the pilot's chair. It's the seat the pilot is sitting in. That is what's actually pushing the pilot forward. So, as the plane accelerates, that chair has to push the pilot forward to make the pilot maintain the same acceleration as the plane does to keep the pilot moving along with the plane. All right, excellent. Let's stick some numbers in another problem. For this problem, Dr. Strange is playing tennis. If you've never seen anyone play tennis before, play it with a big racket. You throw a ball up, you hit the ball with the racket. Now, in this case, we have a ball with a mass of 58 grams. And Dr. Strange hits the ball with the racket. We'll assume the ball is initially at rest. It's initially stationary. She hits it with a racket, and the ball accelerates to a speed of 45.0 meters per second. The racket remains in contact with the ball for a distance of 44 centimeters. Now, the question is, what force does the racket exert on the ball to make it accelerate? So, what's going on? The ball is accelerating from rest to a speed of 45 meters per second over the distance of 44 centimeters. And it has a mass of 58 grams, and the question is, what force is exerted on the ball? Well, let's think about this. How are we going to determine the force? What are the steps that we're going to go through to try and solve this problem? We need to figure out the force. That's what we're looking for. How do we find the force? We have to ask ourselves, what do we know about a force? Well, we know that F equals ma. To use that to find the force, we need two things. There's our equation that's got the force in it. What else do we need? We need to know everything else in the equation. So we need to know m, and we need to know a. Well, we have m, so we need a. We need to figure out what's the acceleration of the ball. How do we find that? Well, we know certain properties of the motion of the ball. It's accelerating from rest to a speed of 45 meters per second over a distance of 44 centimeters. So we're going to use that to figure out the acceleration. We need to go back to our one-dimensional kinematic equations. Just knowing how the problem is stated tells us all we have to worry about is this one-dimensional motion. We need to go back to the one-dimensional kinematic equations, use those to solve for the acceleration. Once we have the acceleration, we can solve for the force. Well, which one of those kinematic equations will we use? Let's just try and think about that. What do we know? We know the ball is starting from rest. We know the initial velocity. It's accelerating to 45 meters per second. That's the final velocity. It's accelerating over a distance of 44 centimeters. So if we put the origin at the initial position, it moves to a final position of 44 centimeters later. Well, what equation could we use to solve for the acceleration? If you think about those four equations, we're going to use the last one, the fourth equation. Excellent. We've got a process that we're going to use. Let's do that. We're going to use the fourth equation to solve for the acceleration. Once we have the acceleration, we'll have the force. Let's do it. Here we have that fourth equation. V squared equals V naught squared plus 2a times x minus x naught. Now, there are different ways that we might solve this. You might stick all the values in and then manipulate the things around to solve for what you want. Or you might manipulate the variables first and then put the numbers in. I kind of like to do a little combination of both of those. I think it makes it a little more accurate when I want to finally calculate those numbers. What I like to do is stick in any easy values, in particular zeros, then I manipulate the variables, then I stick in all the rest of the values for those variables. So what do we know? We know the initial velocity of the ball is 0, so I'll say V naught is 0 right in the beginning. So we can just get rid of that. Now, solving for the acceleration, what do? We have to divide both sides by 2 times x minus x naught. So we end up with a equals v squared divided by 2 times x minus x naught. V, the final velocity, we know is 45 meters per second, divided by 2 times x minus x naught. That's the distance traveled, which we know is 44 centimeters. Converting that to meters, 0.440 meters. Dividing that out, we get, on the calculator, you'll get something like 2,301. But keeping that to 3 sig figs, that would be 2,300. But how do we write 2,300 with only 3 significant figures? We need 1, 2, 3, 1, 2, 3. Let me just mention again that this 2 from the kinematic equations, that is an exact value, so we don't have to worry about how many sig figs the 2 has. But we've got 3 and 3, which means our final answer should have 3 sig figs. How do we write 2,300 with 3 sig figs? Well, like we went over in the very beginning, we'll need to write that in scientific notation. So 2.30 times 10 to the 3, and then what are our units? Well, notice what do we get? We're going to have meters per second squared, which gives us meters squared per second squared, divided by meters. One of the meters cancel, we end up with meters per second squared. Meters per second squared. Or we could just remember that as long as we put in everything in SI units, our answer has to come out with the correct SI units, and we know the correct SI units for acceleration are meters per second squared. There we go. 2.30 times 10 to the 3 meters per second squared. We want the force, so what's our force? F equals ma. The mass, 58 grams, again, converting that to kilograms, 0.0580 kilograms times 2.30 times 10 to the 3 meters per second squared, leaves us with a final force of 133 kilogram meters per second squared, newtons. Excellent. Now, the last law of Newton, Newton's third law. Let's take a look at that.